Hello everyone, and welcome to the first session of the WEST program on active transportation and shared mobility at BTR8. I am Negin Ali Soltani, assistant professor from University Gustave Eiffel in France, and I will be chairing this session today. Thank you all for joining. And we have a very interesting session with six presentations on bike sharing, shared micromobility, walking, micromobility hubs, multimodal accessibility, and low stress cycling. And our Zoom coordinator today is Surav Pokharel, who will help us with the technical matters that we have during this session. So we have 2 hours for this session and six presentations. So each presenter will have 15 minutes for the presentation, followed by 5 minutes questions and discussions. So to help us stay on time, I will give a short reminder when the presentation time is almost finished. And please keep your microphone muted when you are not speaking. And for questions, you can use the chat in the Zoom or raise your hand during the discussion time, and I will try to take questions after each presentation. So let's start the first presentation. The first presenter is Yeji Jeon. Yes, so they have to adjust their camera so we can see their faces. I don't know if the first presenter is ready. Okay. Thank you very much.
Okay.
The floor is yours. Please go ahead.
Thank you. I'll try to... Hope everyone can see my screen well. Are we good? And can you hear me well? Okay.
Just a small point, we can see the
Yes.
presentation mode. So
Yes.
yeah, if you want, you can
Oh.
change it. Yeah, we can see the notes section.
Okay, yeah. Thank you for pointing out that. Okay, sounds good. Okay. Hi everyone, I'm Yeji. I am a third year PhD student in the University of Arizona. Today, I'm really happy to share one of my research topic, which is on understanding user retention in bike sharing systems with the survivor analysis with different factors, including operational, environmental, and demographic influences. In today's the research, we are mainly focused on new pricing plan introduction, which I will introduce further. So, to go over a brief introduction about this research, I believe most of you are already really familiar with this bike sharing system, but I would like to introduce once more. Bike sharing system has been emerging as an economically viable and environmentally sustainable mode of transportation. And this has a potential to replace first and last mile connectivity, which can improve accessibility and which can improve like transit-oriented developments. And in Tucson, where I'm currently living and studying, we have a bike sharing system called TuGo. And we were looking at this data, and then we found this one unique opportunity that actually this pay-as-you-go casual pass type was introduced during the operations, while other pass types were there since they started the data collection. So we thought that maybe we can look at this pass type and we can see how people behave differently. So I'm assuming that most of you are not really familiar with Tucson. So I want to show a little bit about how the Tucson looks like. So as you can see here, we have really, really high car commute share. Most of the neighborhoods has like over like about 90% of car commute share. And compare this to transit and bike commute share. Transit we have more sparse, but like still we're have around like 0 to 17.5% common share, and for bike we have around like 0 to 16%. So relative to this, we can see that our city is characterized as very auto dependent, and we have like low density development and dispersed activity center. Considering like when I go to somewhere, some locations, I want to go somewhere, it takes usually like 20 minutes drive. So we can see like it's really low density development city. So this brings up a challenge of long-term sustainability of shared mobility systems. And then we did some literature review how other literatures has been explored this new pricing plan, especially casual pricing plan introduction. And we found out a research gap that prior studies, they were mainly more focused on economic benefits and immediate travel behavioral effect of pay-as-you-go using simulated or survey trip data. And after we reviewed our data, we found out we can contribute by examining impact of pay-as-you-go on user loyalty using observed data, reflecting sustained service participation by using each person's trip history. So to do this, we have to collect different data sources because we do not only want to measure just about the pay-as-you-go introduction, but we also wanted to see with other different attributes also. So we got this multi-source data, and we categorize into three different factors categories. First is internal factors, which is more about operational factors. And the first variable is if the user was introduced before pay-as-you-go was there or not. And second one is we also wanted to see the history of their travel before the COVID. And then we wanted to see the average trip cost. And we also wanted to see if the person ever used subsidy-based pastime. And then the second category is geographic built environmental category versus multimodal accessibility. And next is we also wanted to see if the more retail available there can not improve, associated with the longer use of their bike sharing use. And street-wide, nearby their trip beginning location and sidewalk existence also nearby their trip starting locations. And the last category is the demographic and safety related versus traffic incident counts around the locations that they started their trip and non-vehicle owned household around the neighborhood that they started the trip. So with this, we ended up with these variables, but the first time when we initiate data set was used to have like 200 variables, but we tested with the p-values and then we selected this set of variables as statistically significant variables. And so with this data, we first wanted to see how the pattern looks like and how the overall data looks like. So the first, we wanted to see the monthly pattern of trips and users counts. And there were two things that we could point out. The first is I believe most of the locations experienced similar patterns. During pandemic period, we saw that usage dropped. And then another interesting thing that we could observe was when the pay-as-you-go was introduced, we could see the increase in number of new and unique users. However, for the trip counts we considering the seasonal factors, we couldn't see any like significant changes. So we found that user growth and trip activity was following different patterns. And after we were looking at this trip and user counts, we also wanted to see how the pastime changed for each user. And then we found that we wanted to point out two different pastimes. First is pay-as-you-go. We saw that pay-as-you-go attracted a lot of new users. So before pay-as-you-go was there were four different types of casual passes: daily pass, explorer pass, one way to go, free ride passes. Compared to combined new users that were introduced with these four different pass types, pay-as-you-go itself introduced more users than they did. So we saw that this has served as an entry point for future long-term pass users also, because we could see some of the users from who were introduced using pay-as-you-go, they actually went into long-term passes like monthly pass and annual pass. And another pass that we want to point out is long-term pass. We saw the stronger continuous usage when people were using long-term pass, and we could see a role of commitment-based plans supporting more sustained riderships. And moving on to next preliminary analysis, we also wanted to see how the 5Ds with 3 generations looks like using the map. So the first thing was a household without vehicles. We saw that stations in higher shares of non-vehicle households show higher trip activity. And second is street-wide. We saw that stations close to wider roads tend to have lower trip volumes. According to the literature review, people who take bike, if the road is wider, then they usually feel less safe. So that can be one possible reason behind that. Next is multimodal accessibility. Areas with strong multimodal access were associated with higher bike share activity, and retail density. Stations near higher retail density exhibited increased trip frequency. And next, variables that we explored are insignificant variables. So these are the variables that we explored but found as insignificant, but they were usually found significant in other literatures. So we wanted to look these in also. We saw that low-income households, we found that stations within similar lower income ranges showed varied trip activity, and that can show as insignificant variables in our model. And next is housing unit density. Most stations were falling into very similar density range, so that can be one reason back there. And average maximum temperature, since we were exploring the same city, they have very similar temperature experience. So it was relatively uniform. And the last variables we explored was maximum vehicle speed. Stations with different nearby speed limits exhibited similar trip counts. So we kind of tried to look at these data sets and how come these variables were not really being significant in our models, and this map showed explain some why these were not really significant in our model. So moving on to the method and the results part. So we use a model called Cox proportional hazards model, which is survivor analysis model. What this model does is this analyze how different factors affect the timing of event. And how we define inside of this model, how we define the sample is, so this red line is when the pay-as-you-go is introduced, and this blue box is the data period that we selected to collect the samples. And this is like before and after of the 7 months since the pay-as-you-go was introduced. And then after those 7 months are done, it's around like 2022 November. And after that's done, we observe for 5 months if the sample collected from this sample selection period were ever re-showed in the system. So we assume that if the person never showed up for 5 months, which is more than 1 semester, then they might have decided to not continue the service. So that's one assumption that we put in this model. So according to our results, this is our result table. First, for operational factors, we found that if the users were introduced before pay-as-you-go was there, then they were more likely to continue their service. And if they ever had like higher frequency before the COVID was there, like their travel history shows that they had like higher frequency, then they were more likely to continue their service. And if they ever had a to go for all experience, subsidy plan experience, even though the coefficients was really small, but still the statistical significance was pretty pretty good. So this also showed like if they ever had experience with the subsidy plan, they were more likely to continue their service use. And if their trip cost was higher, average trip cost was higher, then they were less likely to continue their service. And next is the built environmental factors. First, if their multimodal accessibility was better, and if the retail density was higher, and if they had the sidewalk existing right next to their trip beginning locations, then they were more likely to continue their service. However, if the street was wider, then they were less likely to continue the service. And for safety related factors, if there was more traffic happen around the areas that they serve their troops, then they were less likely to continue their service. We can see the safety concerns around there. And if the neighborhood around the start beginning locations, then they have higher population of dumb vehicle owned household, then they were more likely to continue their service. So in conclusion, our research contributed by introducing user retention as a key outcome compared to like immediate effect of new pricing plan introduction. We wanted to see more of user retention, how people survive by observing their travel history. And in bike-sharing policy and evaluation using Cox proportional hazard model with integrated data using multi-source. And we found that pay-as-you-go's impacts users who joined before pay-as-you-go was there. They tend to show more sustained usage. They were more likely to survive inside of bike-sharing systems. And pay-as-you-go effectively attracted new users, but mainly function as an entry mechanism. However, we also saw that potential, a part of it's still small, but we still saw that potential that pay-as-you-go introduced user were actually leading to long-term users. So we still see the potential, and it successfully attracted new users. And we also found that by examining different factors with different categories, we found that operational, demographic, and built environmental factors should be integrated together to encourage sustained bike sharing usage. So thank you for listening. And if you have any questions, I would love to take.
Yeah, sorry. Thank you very much, Yeji,
Yeah, thank you.
for being on time. So please raise your hands or put your questions in the chat if you have any question. Okay, I don't see any raised hands. I have a question. Because, okay, we have a question in the chat. I will ask it later. So how did you control for the attitudinal factors of the users?
So we basically use this data set, which is like showing all trip histories. And what this data set has is where they begin and ended their trip, since it's the docking based bike sharing systems. So we could get the travel histories, and it also had like user ID there, which allowed like vertical track within the data set. So we use those data set to combine the user profile.
Okay, thank you very much. So I have a question because the data that you used was for before COVID and everything that happened. But during COVID, we know that a lot of change happened to the transportation system and the behavioral aspect of transportation. So how do you think COVID-19 has changed all the conclusions that you had based on this study?
So our study, yes, we were aware that like during COVID, everything was different. And so we tried to select the samples outside of COVID period. It was like we started our selection period when students were all back in university and people were mostly back in normal. So we tried to set like those time period. However, from our observations, just like overall changes that COVID brought, we found that from preliminary analysis, before COVID, there were more users compared to after COVID was there. So we still saw some reduction in bike sharing use even after like people were back in normal. Yeah.
Interesting, because
Mhm.
the shorter trips like were
Yes.
increased was increased after COVID. So like during COVID because of the lockdown and everything. So it is
Hmm.
interesting.
Hmm. I think it can be mainly also because the drop in during COVID was um a lot of users in Tucson is mostly like students, and during that time university was like locked down, no one was there, so that can be one cause, I believe.
Thank you very much. Any
Thank
other
you.
questions? So maybe we can move to the next presentation. Thank you very
Sounds
much,
good.
Yeji.
Thank you.
So the next presentation is on shared micromobility, and it will be presented by Maria Kajava from Aalto University. Maria, do you hear us?
Yes,
Okay,
yes,
please
can
go
you hear
ahead.
me? Mm, my name is Merja Kajava. I'm a doctoral researcher at Aalto University in Finland. And I will present today our recent study on shared micromobility market comparison from 52 countries. And before moving forward, I would like to thank co-authors Miloš Mladenović, Elnert Coenegrachts, and Joris Beckers. Shared micromobility has gone big changes and has faced rapid global evolution in the past years. There are new vehicle types, e-bikes, e-scooters, cargo bikes, e-mopeds, and new ways of parking these vehicles, and new business models with lots of private companies entering the market. But there are also issues with these micromobility vehicles. The cities are encountering parking issues with these free-floating vehicles. As you can see here, this photo was taken 4 years ago in Oulu, Finland, and you can see the bike lane is fully covered by these vehicles. Same thing for the pedestrian sidewalk. You can't walk here at all. There are limited studies on shared micromobility on an international scale. Our study tries to get a better understanding of this evolution of shared micromobility and its relation to technological diversity. And we try to analyze and identify what trends are emerging internationally in different markets. And we also try to see that what are the similarities and what differences exist between these micromobility services in different countries. Let's first take a look at the key components in the shared micromobility ecosystem. First, there is an operator that manages one or more micromobility services in specific regions. That can be a municipality or an urban area or even a nationwide area. And a micromobility service in a specific location may offer one or more vehicle types to be rented. And these vehicles can be parked in, for example, docking stations, or they can be free floating or some kind of hybrid form. So these are the key entities which we are also covering in our study. This study is based on open data and open standard data, GPFS data, which is General Bike Share Feed Specification. This dataset consists of over 1,000 micromobility systems around the world, and this map shows the number of services in each country which are included in this dataset. And the largest number of services in this dataset come from Germany, France, and United States. The data availability is based very much on the data policies in a specific country or even an urban area, and also by the willingness of the operators to share open data in this standard format. And as you can see in this map, there are some countries where this open data is not available at all, namely China, which is the largest market for micromobility. Nevertheless, this dataset still provides a reasonable coverage into the micromobility services. The raw data includes these systems, vehicle types, stations, and also some background details for the countries. And this data was enriched and then analyzed with multiple methods. For example, 3 types of cluster analysis and network analysis was applied, for example, to identify the operators and countries. And based on these methods, we were able to get some metrics for the systems, the operator typology and system typology. Let's now look at the findings. And one is related to the micromobility operator types. We identified 3 types of operators. First, with the multinational operators that manage systems in several countries. Actually, in this dataset, even in several continents. Then we have national operators which operate systems within a single country. Some national operators are affiliated with the railroad companies, for example, in Germany and Netherlands. And the regional operator is managing locally in a specific region. And this is the largest number of operators in this dataset. As a result of network analysis, we created a network of operators and countries. And this figure shows the largest connected component. This is called the giant component. And this includes almost all the operators and countries in this dataset. The orange bubbles, they represent countries, and the blue colored bubbles, they represent the operators, these 3 types of operators. And the size of the bubble shows that how many systems this bubble, the country or the operator handles. And the edge, which is the connection between the country and operator, this represents how many systems, for example, a specific operator manages in a country. And the countries are very different when you look at this map. For example, France appears to have lots of regional independent operators. And on the other hand, in the middle of the diagram, you see the Germany DE, which includes a small number of operators, but they are very large multinational companies. And here is network measures for this network diagram which you just saw. And most of the operators or countries are just connected to one node. And this means that this actually shows to have a long tail. And a handful of operators or countries have a large number of connections. Another finding is related to the vehicle types. This figure shows the number of, or the share of systems for the past 3 years and the share of vehicle types. And you can see the bicycle scooters are dominating, but the two gray bars here show an emerging vehicle types, namely the cargo bikes and the e-mopeds. And they are slowly getting more ground. And it's good to remember that the micromobility service can provide multiple vehicle types. That's why the percentage goes over 100 when you look at these numbers. And when looking in more detail by country, how these vehicle types are spread out, there are some country-specific differences. First, you can see the proportion of the systems. They are reflected in the bicycle scooter numbers. But then you also see these cargo bicycles on the right-hand side. The DE means Germany, so the cargo bicycles are getting more ground in Germany and Switzerland. And the e-mopeds are appearing in the Netherlands. NL is the ISO code for the Netherlands. And this is because e-mopeds and e-scooters have been forbidden in the Netherlands. That's why the e-mopeds have been replacing the e-scooters. When looking at the different parking types for the micromobility vehicles, this chart shows 3 past years, the absolute number of systems in the datasets and what types of parking modes are provided. And you can see that the free-floating vehicle systems and the virtual, the docking based systems are increasing slightly, but the yellow line shows the virtual stations rapidly increasing. The virtual station is a dedicated drop zone where you have to park the vehicle. And this is something which has been now taken more into use to regulate the parking in Europe, especially in the densely populated city centers. And these virtual stations is now phenomenon, especially in Europe, not yet seen in the United States or South America in this dataset. In summary, the technological diversity is increasing when considering the vehicle types with the bicycles, e-bikes, e-scooters, cargo bikes, e-mopeds. Some systems even had hand bikes and tricycles. And the parking types are now not only the docking stations or free-floating vehicles, but now the virtual stations are one possible way of managing the parking. So, as a result of this study, we have a couple of policy recommendations. And these are for the public and private stakeholders. So when planning a tendering process, cities could also consider additional vehicle types, such as cargo bikes and e-bikes. Cargo bikes, especially for the household last mile logistics, and e-bikes for longer commuting trips. And the virtual stations provide a very cost-effective way to reduce parking issues in the city centers. This also was taken this summer in Oulu, and you can now see that the virtual station has really improved the parking situation. So it's possible to cycle again on this cycle lane. For future research, the availability of the open data is important, especially in standard formats, such as GPFS or MDS. And a good data coverage would allow even further comparisons for shared micromobility services on a global scale. This was a very brief introduction to the micromobility market comparison. Our study was just recently published and it is available with open access. So you can scan the QR code and look at the paper if you want to know more of these results. Thank you for your attention.
Thank you very much, Maria, for your presentation. We have a question in the chat. They have asked, is there any evidence of increasing numbers of adaptive shared use bikes for people with disabilities?
This is a very good question. It was actually surprising to find that the shared micromobility systems even provide hand bikes, which means that you can add an extra bike in front of your wheelchair. But this was very marginal right now, but this is maybe slowly coming in place.
Thank you. Is there any other questions? You can raise your hand and ask the question or put it in the chat. So I have two questions. Thank you very much, because this comparison between different countries is interesting. But how do you think, considering the infrastructure of transportation in different countries, the quality of public transportation system, car ownership, and all the other metrics that we can use to evaluate the quality of transportation and accessibility can impact the result of your work?
This is something which should be in the future analyzed in further, because the countries are so different, and
Yes.
even the climate affects. For example, in the Nordic countries, the snow prevents or reduces the use of micromobility during the winter time when you have snow and slippery, and of course the density of the cities, the public transports, also the being used to cycling or scooter, that's not happening everywhere. So there are lots of other factors which are affecting.
It would be interesting to consider all these factors as well. I had another question. How come in some countries the trend is toward like more bigger companies for the entire country, and in some other countries it is going to be more regional operators like in France. Why do we have this difference?
One kind of result is that the private companies are providing e-scooters. These are not typically provided or sponsored by the cities or the public authorities. So this is one case, and the data for bike sharing systems is more readily available. So the e-scooter data is not fully covered here, with the exception of Norway and Switzerland, which has the full coverage for all the micromobility modes.
So you mean if we have all the data, the results would be different?
With regards to vehicle types and the percentage in a country. And this is indeed because of the data coverage is very different.
I see. Thank you very much. Any other questions? Okay, thank you, Maria. We can continue with the third presentation, which is on assessing the relationship between road networks and walking by Polycap Chebe from Technion. Yes,
Hi,
please go.
I don't know whether you can see my slides.
Yes, it's okay.
Okay.
I just see, okay, it's okay. Please go ahead.
Okay. Hi to everyone. So I'm Polycap Chebe, a PhD student at the Technion Israel Institute of Technology under the supervision of Professor Karen Martins, who is also co-author to this presentation that I am about to make. So I will be presenting on the topic assessing the relationship between urban road design, sense of place, and walking, which is part of my PhD research. Before I get into the presentation proper, I would like you to take a look at these two streets and imagine that these two streets are close to your home. Which of these streets would you prefer to spend time more on? I will not ask you to tell me your choice now, but maybe at the end you can do that. But what I am sure or certain of is that your choice of the streets to spend more time on will depend not only on the movement function of the street, but also on how you perceive the street in terms of it being a place. Now back to my research. As we all know, urban roads serve both as movement corridors and as places for socialization and other economic activities. And in most cases, the design of urban roads will determine which of these functions is prioritized in them. From research, we were made to understand that while there is large-scale research on how roads serve as mobility corridors, there is limited research on how roads function as places. The review that we also did also made us to understand that while there is research that assess that while there is limited research that assess the relationship between streets as places and walking as a mode of transport, which we presume to be more close to the walking environment as compared to other modes of transport. To the extent where this relationship is analyzed, we discover that most of the studies established a unilateral direction showing that the perception of a place highly influenced walking behavior. This brief background was very important to us in framing our research, which seeks to measure street level sense of place and assess its reciprocal relationship with walking behavior, with two questions that we had. The first question was which urban street designs are associated with high level of walking level of sense of place. And then the second question was how is sense of place and working frequency associated under different alternative structural specifications. So from these questions, we came up with this conceptual framework in which we show that the design of urban roads influence both working frequency and sense of place, while also controlling for socio-demographic characteristics. As I said earlier, research has already shown that there is an association from sense of place to working frequency, but the question is on whether working frequency is also associated to sense of place. So in order to address this issue, we adopted a case study approach of 5 urban roads in Addis Ababa, 2 upgraded streets and 3 non-upgraded streets. We conducted a survey with over 256 respondents living along the 5 streets, which I will show you shortly. We use a 17-scale sense of place dimension grouped into 3 dimensions: place dependence, place attachment, and place identity to measure sense of place. And then we measured working frequency or working behavior in terms of reported weekly working frequency. And finally, we used 3 structural equation models to examine the reciprocal association between sense of place and working frequency. So for the structures of the model, the first model, we specified sense of place as a first order dimensions with 3 variables, that is place dependence, place attachment, and place identity, directly estimating working frequency while controlling for a street category, which was included in the model as a proxy for land use activities and socio-demographic characteristics. In the second model, we specify sense of place as a second order Latin variable, estimating working frequency while still including street category and socio-demographic characteristics as control variables. And in the third model, we reverse the structure of the model by looking at the association from working frequency to sense of place while still controlling for street category and socio-demographic characteristics of the respondent. And then for the sense of place tool that we use, which I am not going to dwell much on it, as I said, we had 3 measurable dimensions. The first one was place dependence, which had 5 indicators. The second one was place attachment with 6 indicators. And the last one was place identity, which also had 6 indicators. And just to say that these indicators were drawn based on existing literature, particularly those of Jorgensen and Statesman, who have widely researched sense of place in the past, and other associated studies on sense of place. Then this is just an excerpt of the streets that were selected. So for the unupgraded streets, we had 2 of them. As I said earlier, the first one was the Sierra Leone Street, which is locally known in Addis Ababa as Gotera. And then we had the Gergi streets too. And these were some of the place activities that were going on along these streets. Then for the upgraded streets, we had 3 of them. We had the Côte d'Ivoire Street, which is locally known as Megangaya. And then we had this African Avenue Street, which is locally known as Bole Street. And then we had this 3rd street, which is the Bole Michael Street, that was recently upgraded with the flyover section and then some chairs provided under the flyover. So for the result of the descriptive analysis that we did, the first thing we observed was that there were significant variations in sense of place score across the different selected streets and neighborhoods. But when we look at them closely, we discovered that there was no significant variation in terms of sense of place score between each street and its associated neighborhood. Then in terms of the different streets, we observed that the best street, or the street with the highest sense of place score, was the African Avenue Street, which was an upgraded street. And interestingly, we also found that the street with the lowest score was also an upgraded street, which was the Côte d'Ivoire street. And then for the 3 dimensions, we discovered that place dependence consistently was scored lower as compared to place attachment and place identity. While for working frequency, we observed that there was no significant variations in working frequency across the 5 streets. Then for the model analysis that we did for the first model, these were the different variables that we included, and as I said, the first model, we specify sense of place in terms of the 3 measurable dimensions, which included place dependence, place attachment, and place identity, directly predicting working frequency. And for the results, we discovered that among the 3 dimensions, only place identity showed a significant positive association with working frequency, while place dependence and place attachment was not significant. For the exogenous variables, which were included as control variables, we found out that the variable related to age was positive, in which older adults reported working more frequently compared to younger adults. Then for the second model, in which we specify working frequency as a sense of place as a second order Latin construct predicting working frequency, we found a significant association from sense of place to working frequency. And in this model, we found that the dimension of age too was significant, while the other included variables were not significant. Then for the last model, in which we reversed the structure of the specification from working frequency to sense of place, we found that there was a significant association from working frequency to sense of place. And this time, the included street category variables were significant compared to the previous model. So overall, the study showed a significant variation in sense of place across the streets, with the highest and lowest sense of place score observed along upgraded streets. And for the model analysis, we were made to understand that sense of place and working frequency are positively associated with place identity, indicating the strongest association with working frequency. And then the last 2 models showed a positive association between sense of place and working frequency, suggesting the existence of a potential bidirectional relationship between sense of place and working frequency. For the limitations of the study, the first one we want to acknowledge was the number of participants, which was not fully representative. And for future research, we suggest using a larger sample size. And then we also acknowledge limitations in using self-reported data to measure working frequency, which may not actually reflect actual working behavior. And maybe in future studies, we recommend using or conducting actual counts, maybe using modern equipment like cameras and so on, or doing manual counts. And then we also acknowledge limitations in the cross-sectional data that we use in the study, which limited our ability to fully establish whether there was a bidirectional relationship between sense of place and working frequency. And so for future research, we recommend considering using longitudinal data, which can confidently assess and confirm whether such relationship exists. Then for final observation, while the study shed light on understanding the relationship between street design, sense of place, and working, it also suggests that working and sense of place appears to be embedded in social, experimental, and spatial characteristics of everyday streets. The study also suggests that a walkable street may not necessarily be a meaningful place, and a meaningful place may not necessarily be a conventional walkable street. So this may be important for transport planners seeking to develop more walkable streets to consider, especially when planning streets, to rethink of their design, not just as mobility corridors, but also as places for different socio-economic activities. Thank you very much for your attention. If there are questions, I will take them.
Thank you very much. So please raise your hand if you have a question or put your question in the chat. Okay, I have a question because you concluded that the identity was the strongest factor, right?
Yes.
But why do you think you had these results? Why identity is the most important factor, has more impact?
All right. So intuitively, since we did not actually do some sort qualitative findings to see why this happened, but intuitively we may be thinking also in the results may be context specific, maybe based on the case of Addis Ababa and maybe other sub-Saharan African cities in which in most cases, when you look at how the cities are structured, they mostly have central business districts in which most activities take place there. And so in terms of place dependence, people may not really depend on their neighborhoods that much, but more of the central business districts. And so likely, and then when we look at the elements that are linked to identity, which show some sort of personal connection, this is my street, these elements, people may experience them more as compared to maybe the dependence and some sort of attachment. For now, that is maybe my intuitive implication of why I think the identity was significant, while the others were not. Yeah.
So if you want to have some recommendations to the planners, like in Addis Ababa, do you recommend them to focus more on pedestrian infrastructure or identity and attachment to the streets or public spaces?
Okay, so what happened is, because also based on the observations that we did along the street, that we did since we conducted the research there, we observed that in course of doing upgrading of the streets, in most cases, some place activities were displaced, especially informal livelihood activities that used to take place along some of these upgraded streets. And with the displacement of these informal livelihood activities, the vibrancy of these streets was largely reduced. So in planning, the two needs to go together. Sometimes when you prioritize the movement function, trying to provide working facilities without also ensuring the vibrancy of the streets, then you are going to lose the aspect of the streets as a place greatly. So I think the two needs to go together. If you focus more designing walkable streets and thinking you will achieve the goal of sense of place, that may turn out not to be the case, as based on what the results show. And sometimes too, as I also said, some meaningful places may not necessarily be upgraded streets. We saw some of the basic streets with high vibrancy. People show high, people had reported them to be higher in terms of sense of place. So I think the two needs to be embedded together in order to design streets that are not just movement corridors, but also places that people can relate with.
Thank you very much. Any other questions? Okay, so we can continue with the fourth presentation, which is on micromobility hubs by Panagiota Mavrogenidou. I hope I pronounced it correctly.
Yes. Hello. Just give me a second to share my screen.
Yes, sure.
This one. Can you see my presentation?
Perfect. Yes, thank you.
Okay. So, sorry. Hello, everyone. My name is Panagiota Mavrogenidou. I am a PhD student from the University of the Aegean in Greece. Today I'm going to present you a collaborative work between our university and University of Leeds with Professor Charisma on the potential of micromobility hubs for urban areas. 55% of the global population lives in urban areas, with this share reaching 80% in high-income countries. Which has resulted in micromobility gaining attention as a flexible solution to urban congestion. This specific study focuses on the United Kingdom. So according to TomTom 2024 traffic report, the average driver in London loses 113 hours in traffic in London. While for the United Kingdom, when compared with the European countries, it ranked as the 5th most congested country. There's an ongoing debate on whether microcars should be considered a form of micromobility. According to the International Transport Forum, micromobility are lightweight devices, vehicles with a maximum design speed of 45 kilometers per hour and a maximum weight of 350 kilograms. Most famous commercial microcars, such as the Citroën Ami or Microlino, fall outside of the ITF's weight limit. However, there are others, less known, that meet or closely align with these thresholds, supporting the inclusion of microcars in the micromobility definition. You can see in the table 4 examples with the weight, the maximum speed, and the seats that the car has. In addition, even the most famous and that fall outside of the threshold microcars, such as Citroën Ami, are classified as L6E vehicles and can be driven with a MOPT license, driving license, and not a car driving license. So, given the fact that there are some microcars that fall into the definition of ITF for micromobility, and regulatory similarities with MOPs that are already treated as micromobility, we consider it that we should examine the potential benefits of including microcars into the wider definition of micromobility, and to examine how microcars could help support a safer ecosystem. This work also focuses on mobility hubs. A mobility hub is a clearly identifiable area where different public and shared transport modes are brought all together and connected to increase accessibility and improve users' experience. In our case, that we examine micromobility hubs, we defined it as permanently connected areas that integrate shared micromobility services with public transport. So we exclude services such as car sharing, services such as ride-hailing with Uber, for example, or taxis. We focus on short distances and first and last mile connectivity, and we try to examine users' evaluation of micromobility hubs as a distinct system and not as a component of a wider mobility system. We examine how infrastructure, safety, and users' characteristics jointly influence users' mode choice. And we also examine users' preferences and trade-offs relevant to the design and implementation of such hubs. Our study started, of course, with a literature review in order to identify gaps, define the research question and the survey design. We proceeded with the survey design that we included stated preference experiments, a travel behavior diary, perception and attitudes, and of course demographics. In total, we used 3 different data sets for our model. We used the survey data, some OpenStreetMaps data for cycling infrastructure data, and road accident data. All these 3 components were combined into our final model estimation. For our stated preference experiment, at first the scenario was presented to the respondents. More specifically, we showed them the trip purpose, the weather conditions, and the area and the speed limit for their area. And we asked them what mode they would usually use for such trip. And then we also asked them whether they would consider using a micromobility hub for their trip. Those that responded yes, were shown the Micromobility Hub choice task, while those that responded no were shown an alternative choice task that was related to public transport services and some shared services in the city. So this process was repeated across all 6 choice scenarios, resulting to some individuals answering more Micromobility Hub scenarios and fewer public transport scenarios, and others the opposite. In this presentation, we focus only on the Micromobility Hub choice task, and the public transport choice task is not examined at all. Here you can see the attributes of the Micromobility Hub experiment. We examined waiting time, travel time, walking time to the final destination from the final station, cost, bike lane existence in the trip, charging level of each vehicle, some additional features such as the provision of helmet, SOS buttons, etc. And also for the additional provided information that were shown in the beginning and were fixed for all modes, the trip purpose, weather, and the speed limit. You can see for trip purpose, we examined shopping, leisure, work, education, errands, or visiting another city. On the right, you can see a screenshot from our stated preference scenario. The final option, people could actually say that they would choose their current transport mode. So in the end, we collected 500 questionnaires, 500 respondents. We used quotas on age, gender, region, and income. For the hub stated preference scenario, we had 346 respondents participating at least in one scenario, answering that they were open to use a Micromobility Hub at least in one of the scenarios presented to them, and in total we had 1,387 choice observations. Gender and age, you can see in the diagrams, they follow the UK distribution since we did use the quotas for these variables. 75% of our sample were employed, only 6% of our sample were students. You can also see the distribution of education, with 34% holding a university degree. And you can also see the distribution of our sample in different regions that also follow the UK distribution due to the quotas that used in the survey. We also asked them about their physical activity. You can see that 65% did state that they exercise often during each week. And we included some indicators on Micromobility Hub attractiveness for each respondent. Some statements about whether they believe a Micromobility Hub will help with the economy, the sustainability of the area, parking spaces, safety of pedestrians and cyclists, accessibility and connectivity. The scale was from 1 to 6. You can see that most of the answers are around 5, closer to 5, closer to 4.5. So the option was quite positive. And we also had some digital comfort indicators, like whether they use their phone for work purposes, whether they consider hard to learn new technologies, whether they use up about the navigation in the city, etc. So now move forward with our modeling. We created a hybrid mixed multinomial logit model with 2 latent variables. We used some variables for the level of service, some contextual factors and demographics. And for our 2 latent variables, our digital comfort latent variable, the structural equation for the digital comfort latent variable was related to previous shared service usage, salary, and age, while for the perceived attractiveness, university degree, the number of kids in the household, cycling network density in your area, and the regional total crashes. For the cycling network density, we utilize OpenStreetMaps data extracted via Overpass Turbo, while for the regional total crashes, we used official crashes datasets from the official national statistics of the United Kingdom. To have a more complete presentation, I've also added the model estimation table. The rho square for our model was 0.25, and the observation, as I said before, were 1,387 observations. We can, if anyone wants to return to this table, we can return. I'll have make a cleaner slide later. Also, the latent variables metrics about the latent variable, the measurement, and the structural equation parts of its latent variables. So for a cleaner presentation, I'll present the results in this slide. So the model, if anyone wants, we can show the previous slides again. So waiting time reduces the likelihood of choosing all hub modes. Travel time showed the expected negative direction, but wasn't statistically significant. Helmet provision was positively influenced when considered alongside the cost of the trip. Higher charging level increased the preference for e-scooters and e-mopes. Older respondents were more likely to return to their usual mode of transport, while visitors to a city were more likely to choose a microcar or e-bicycles. Something alarming that came up from our model was that respondents who would, as I said before when I was describing the stated preference experiment, in the beginning we presented them the scenario and we asked them in their usual life what mode they would normally use to perform that trip. So respondents who would otherwise walk, they were more likely to choose e-bicycles or e-scooters, which is quite alarming since we don't want to shift short walking trips towards motorized modes. So hub design and implementation should carefully address the substitution risk, and it's worth further examination. For our perceived hub attractiveness latent variable, it significantly increased the likelihood of choosing hub-based mode. So making clear to people what is positive about this hub is significantly helps to make them choose to use the hub. Specifically for the latent variable, the higher the education, the higher the perceived hub attractiveness. The more the children in the household, the higher the perceived attractiveness, the greater the local cycling network, again, the higher the perceived attractiveness, while, of course, the higher the regional crash level, the lower the hub attractiveness. For digital comfort, we had a positive but not statistically significant relationship with mode choice. Younger respondents were more digital comfort, higher income respondents and previous shared mobility users were also showed also higher digital comfort. I've also added some links for the pictures used through the presentation. Thank you very much, and I want to also say that this study was made possibly through the Yeji British Short-Term Scholarship Program. It was supported by the State Scholarship Foundation of Greece, Yeji, the British Embassy in Athens, and the British Council in Greece. Thank you very much.
Thank you very much for the interesting presentation. So please, if you have any questions, raise your hand or put the question in the chat. I have a question. It was interesting that you consider microcars as the micromobility services for the hubs because they have like different parking infrastructure. They need bigger spaces. But do you think you should consider them all the time in different hubs, in different network, with different urban contexts?
In general, if every time we discuss about a micromobility hub, we should consider microcars. That's the question.
Yeah, but sometimes like in dense areas, it can be challenging.
Yes.
Yeah.
Of course, this needs to be examined specifically for its location. Locations that have smaller areas and they are not the residents are not too highly dependent on their private car. For example, I have some cities like that in Greece in my mind. wouldn't actually benefit from adding microcars. You need to have the space. You need to have people interested in using them. You need to have you need to examine specifically for each different location if people are interested in this service, and also if the city can support this service, of course.
Thank you very much.
But in some cases, for example, in my city, I think having some microcars reducing the private vehicles could be supportive. Just that.
Thank you. Any other questions? Okay, thank you very much.
Thank you
So
very
we can
much.
continue with the next presentation. We had some technical issues for the last presentation, so we will have a change. We will go with the last presentation on low stress cycling by Peter Furth.
Hello, everyone.
Hello.
Hello. Glad to oh, that's the wrong one. Ay. I thought I had it all ready to go.
Fortunately, we have saved some time with the previous presentation, so don't worry.
It's filling up my screen, so I can't find the ay.
Maybe Saurav can share your presentation, and you can ask him to change the slides whenever you want.
There, I've got it here. Yeah.
Okay.
Okay. It's just that when Zoom is on, Zoom covers part of my desktop, so I can't see. Okay, now it should be good, right?
Yes, perfect. Thank you.
Okay. All right. Hello, everyone. I'm Peter Furth from Northeastern University. Did this research together with a PhD student, Nathan David Obeng-Amoako, who's also well, at least he's listening. We're looking at level of traffic stress now at intersections, which includes some interesting dual graph network modeling. Where we do this research, I think everybody who's involved recognizes that getting people to ride bikes just as an everyday way of getting around is good for people, it's good for the planet, it's good for cities. For the reasons I've shown there and many others. But in most places, the main thing that stands in the way of people using bicycles every day is traffic. It's that automobile traffic makes it stressful and dangerous to ride a bike. So to help understand this and research it more, a little over 10 years ago, I developed level of traffic stress as some criteria with low stress, level traffic stress 1, 2, 3, and 4. The low traffic stress is meant for children and some adults, in which you just don't interact with cars at all, except at crossings and like driveway crossings or intersections. Level of traffic stress 2, which most adults can handle. You have your own space, and you don't really have to interact with fast-moving traffic. Level of traffic stress 3, you have your own space, but now you're having to deal with faster multi-lane traffic. And level of traffic stress 4, you just thrust into mixed traffic on a multi-lane or a high-speed road. And not many people are willing to do that. Looking at traffic segments in our past research, when we classified them by the 4 levels of traffic stress, if you look here at this map of part of San Jose, California, you can see how there's different levels of traffic stress according to the color. And if you're willing to ride on all 4 levels of traffic stress, well, the whole city is yours. You can ride anywhere you want. But if you aren't willing to ride where the level of traffic stress is 4, I erase the level stress 4. That's what the network you have. And now you start to see there's some gaps. There's some islands that you can't get from that island to anywhere else in the city unless you're willing to ride on that level of stress 4. If you only want to handle level of stress 3, the gaps in the islands become more severe. Level of traffic stress 1, even the most, you can see that, wow, all over the city, you just, what can you do? You can leave your home, ride around a couple streets in your neighborhood, and you just got to go right back home. You can't get anywhere. Your accessibility is just almost to destinations is almost 0. So in this research, we're looking at another source of traffic stress, which is intersection crossings. So if you look at the big street in the middle, yeah, that's stressful to ride along. But if you look at the 2 legs on the side, oh, those are nice, quiet, low-stress streets. Wouldn't they be nice to ride on? But to get from the segment on one side to on the other, you got to cross this big street, and that is stressful. So that's going to affect your network connectivity. That's going to affect accessibility. Can you get from here to there? So we wanted to do more systematic study of how intersections have a traffic stress. So the 3 research tasks that we took on and that we'll be presenting here are: number 1, we need some criteria for intersection traffic stress. Is it level traffic? What makes a crossing level traffic stress 1, 2, 3, or 4? We need a network analysis that accounts for stress at intersections, because most networks, the cost, the stress is on the links, not the nodes. But at intersections, those are nodes. So how can we account for it? And then in some case studies, we want to answer, well, and just how significant a barrier is intersection traffic stress. If you've already accounted for segment traffic stress, how much of a difference do intersections make in keeping people from having a low stress ride to their destinations? So first on with the criteria. So some at intersections that are signalized, well, then the crossings are pretty easy. In my country anyway, in the United States, most places where there's a signalized crossing, there's a provision that makes it safer for pedestrians to cross. So if pedestrians can cross, usually bikes can cross also. But still, there are some conditions under which it's higher stress, and we call those triggers. So the first one is crossing distance. If you have to cross more than 30 meters, then there's a chance that while you're only partway across, the light's going to change, other traffic gets a green light. That's stressful. If you're experienced with traffic, like most adults are, you can handle it, but this would not be suitable for kids. And other factors are there, the right turn volume that's permitted to be a conflict with you, left turn volume, the speed at which people can make right turns. I suppose I could put left turns if they're permitted also. And you see this one could trigger level of traffic stress 3. And then the pedestrians have to make a multi-stage crossing. They have to go and cross to an island and then wait there and continue. Those triggers can make signalized intersections higher level of traffic stress than just 1, which is the lowest stress. More concerning, though, are the unsignalized crossings, assuming you're on the non-priority street. And there, the stress of crossing a street, it increases. If there's no crossing island, then it's worse than if there is a crossing island. Speed, if the speed is low, well, then it's less stressful than if the speed is high. How many lanes are you crossing? If you're crossing only 1, 2, or 3 lanes, it's not as stressful as if you're crossing 4 or more lanes. And finally, the average daily traffic, the number of vehicles per day. As the average daily traffic increases, the stress will be higher. So here we have criteria for these unsignalized crossings that could make the crossing level of stress all the way up to level of stress 4. To come up with the parameters for these crossings, we didn't do a behavioral study of, asking people about their feelings of stress, that there's problems in doing that, and we didn't have the budget for doing that. But we did use a gap acceptance model that allowed us to have parameters that would be consistent. So we looked at 3 user classes: children, most adults, and bike enthusiasts. And they have different speeds, different startup offsets, different tolerable post-encroachment times. And then the gap acceptance model would give a maximum average delay, and we imposed a maximum. And that gave us some consistent criteria. So if I step back to the previous slide, that's how we came up with these volume limits that under these other conditions would be acceptable, let's say, for level of traffic stress 1, whereas if you're in this case, if you're over 9,000 cars a day, now you're up at level of traffic stress 2, and so on. Another special case, we found that when there are trails, meaning a bike path that's not alongside a road, but completely on its own, crossing a road, that you can get a pretty low stress crossing because cars will stop for you if the speed is low enough. It depends on speed, it depends on whether there's an island, depends on the traffic volume, and it depends on whether there's a rectangular flashing beacon. So those were those were most of our criteria. Then there's some special cases for freeway ramp crossings. I think everybody understands when you're riding on a road and suddenly there's an on-ramp to a freeway. Oh, cars just zoom across that. It's so stressful crossing those. So crossing on-ramps, off-ramps, there are triggers. And then there's also a trigger from when there's a blind entry. And this is what I mean by a blind entry. You can see here along Salisbury Road, there's a bike path, but the geometry of the corner, because the bike path is right at the curb, when you have to turn to enter the crossing, you don't have a chance to see what traffic is conflicting with you except by looking behind you. And looking behind you is difficult. And people, when they look behind, they fall or they lose their balance. So I call that a blind entry. And that makes a higher stress intersection. Now, when it comes to putting them on the network, here's a network of streets in Boston. And what's typical for a city is that roads are represented by a single line, like you see here, and here's another single line. Well, we want to visualize the stressor at the crossings. Well, the intersection is just a point. You can't visualize a point. So we made these kind of virtual segments just to visualize, and here they're blue to show. Here I have the 4 crossings. Some roads, like this road, Columbia Road, are represented with a dual carriageway, and so there is a crossing link for one of the streets, but it's only in one direction, whereas we want to show the 4 different crossings, one in each direction. At a 3-leg intersection, you see here the 3 crossings. This is the crossing across the bottom of the stem. There is no crossing across the top of the stem, so there's no crossing there. And then what makes an X here, these are the crossings associated with the left turn that you would make going into or out of the side street. But when it comes to a network analysis, we distinguish crossing stress, X LTS, from movement stress. Movement meaning like a turning movement. So a crossing stress, that's the stress of crossing a particular leg, whereas a movement stress is a stress associated with making a certain movement. So for instance, at this intersection, when you're making a right turn, you're not crossing anything. So there's no stress making the crossing. If you're making a through movement, like this through movement going north, you'll be crossing leg 3. So the stress of that movement is the same as the stress of crossing leg 3, which is entirely dependent on characteristics of leg 3, like how many lanes it has, how much traffic it has, whether there's a traffic light, and so on. If you're making a left turn, like the left turn shown here with the purple arrow, you're now crossing 2 legs. We assumed left turns are all movements are going around the intersections, kind of square, going around counterclockwise, like shown here. So in other words, cyclists are making a two-stage turn. They have to cross leg 3, then they wait if necessary, and would cross leg 0. So they have stress crossing the first leg. They have some crossing stress crossing the second leg, and the stress of the movement is the maximum of those two, consistent with the way we've done traffic stress on segments. Then, in order to get the stress of a movement at a node, which there's no in a usual graph representation, there is no cost. You can't put a stress or a cost or a restriction at a node, but there is another way of doing this, which is a dual graph representation, which is used in routing for automobiles. It's been used in routing for public transportation. So it can also be used with bicycling. And with a dual graph representation, first of all, each link has to be represented by a pair of directional links, that is, if it allows two-way travel. So the north-south link is 2 links. And then every movement is represented by an edge. So the edge that I'm pointing to here, going from and let me say, and the nodes in the dual graph are the segments. So the 8 boxes that you see, like 2SB, 2NB, those are the nodes, the dual nodes, and the dual edges are an edge going from one dual node to another. So for instance, this edge going from 2NB to 1WB, that's a movement making a left turn. And now in the dual graph, this edge can be given a cost, and that cost includes the stress of this movement. So I've already talked about how we determine the stress of a movement. So we can put the stress of the movement on this cost. This edge also includes anything about the original segment that leads into it, and not about the segment you go to. So it would include the length of this segment in distance. It would include the traffic stress on this segment. All of that goes into the dual edge. While the dual nodes, now they have no stress, they have no cost, they have no anything. So then when you're doing a routing in a dual network, you use exactly the same kind of shortest path algorithm or other network algorithms that you could use in a standard network. We also, as we do with other level traffic stress accessibility measures, cyclists are not willing to make a long detour, and the willingness to cycle goes down when people have to go a long distance. So we use some propensity functions. There's no penalty for detour for up to 20% of your travel distance, but more than 50% people are just unwilling to do a detour like that. For short distances, people are willing to go on a detour of 300 meters, completely unwilling to go a detour of more than 600 meters, unless it meets the relative criteria. Then for longer distance, that's okay. And then for distance, people are willing to go with no diminution in propensity for up to 6 kilometers, and after that, propensity declines with an exponential decay with a half-life of 2.5 kilometers. When you put those 3 factors together, it creates a propensity region like this. The dark region, that's where the highest propensity is. On the horizontal scale, you see what's the distance you have to go. On the vertical scale is how much detour there is. The detour is in meters, so here's 1 kilometer detour, 2 kilometers of detour. So the highest propensity region is when your trip isn't too long and doesn't have too much detour, and as the length or detour increase, the propensity becomes lower and lower. And then we applied this to looking at accessibility to jobs in Boston. We already had for Boston a level of traffic stress for segments. So we got all the data that we needed to calculate level of traffic stress for every crossing. We then took that a next level to make that the level of traffic stress for every movement. We created background movement links, and then we created the dual network. And then we analyzed, in this case, we're looking at a many-to-one accessibility, accessibility to this particular high school. Where is there low stress, level of traffic stress 1, because we're talking about children going to high school, level of traffic stress 1 to get to Brook High School? You can see it's not too good. I mean, everywhere there isn't either a green or black line, sorry, you have to go on a high stress link to get to that high school. So you don't have a low stress accessibility. But in green, you do have low stress accessibility. And in black, you also have low stress accessibility if you ignore crossings. But there is a crossing where the black and green meet that you'd have to make to get to Brook High School and back home again if you lived in the southern neighborhood where it's black. And that has that's a crossing LTS2. So if you account for intersections as a barrier, then about half of the area that you would think is accessible to Brook High School is not accessible. So the high stress crossing there is creating a barrier to accessibility. We also did that looking at jobs. Jobs, of course, are all over Boston with their homes all over Boston. The Boston area here includes the cities of Cambridge, Somerville, and Brookline, in case you know Boston. So that's a pretty compact area. And looking at the 4 levels of traffic stress, if the crossing LTS is not enforced, in other words, is ignored, if we just looked at it the traditional way, you'd say almost 1% of jobs are accessible to homes if you're only willing to ride on LTS1 segments and you only have a certain propensity for detour and distance as I described. But when you enforce crossing LTS, oh, that percentage drops way back. A lot of jobs that you could get to if you ignored intersection traffic stress, now you can't get to. If we look at level traffic stress 2, which we've said applies to most adults, you can get to about on average, a home can get to about 12% of the jobs in the Boston area. When when crossing traffic stress is enforced, that goes down, not too much, down to a little bit below 11%. So the crossings take away some accessibility, but not nearly as much as the segments do. At level of traffic stress 3, there's hardly any difference because there aren't many level of traffic stress 3 crossings ultimately. And at level of traffic 4, of course, there's no difference because you're willing to ride on anything. By the way, it's worth noting that if we didn't have propensity for distance and detour, this would be 100%. So the fact that it's not 100% is because of the distance propensity. Every job, people aren't willing to travel that far to get to a job. Here's at LTS1, you can see with the same color scale used for both sides. On the left side, we're ignoring crossing stress. On the right side, we're accounting for crossing stress. And the number of jobs you can get to from these different neighborhoods goes way down. So for instance, here you see a big area where a lot of people can get to a lot of crossings that just part of it remains and part of it disappears because getting to them involves a pretty high stress crossing just to get onto the a nice bike network. At level of traffic stress 2, the comparison, it's not so stark. Like I said, it's on average it's 12%. Here on average it's 11% here. So a little bit lower accessibility due to level of traffic stress 2 crossings. So the conclusion is, remember that this research, we had 3 main tasks to look at. One was we needed some criteria for intersection LTS. So we developed these criteria. They just were put on a public website. You're the first people to know about this. It just got published this week on my website here at Northeastern University. Then regarding network analysis, how do you account for level of traffic stress? So, and the solution we said is to use a dual graph. Now, it turns out you don't need a dual graph if every single crossing in the network is already coded as a link. Then you can do it all as just as the regular network analysis. But most city intersections, the crossings are not all coded. So that's why we found it necessary to use a dual graph. And then to answer the question, and how significant a barrier is intersection traffic stress? Well, at least in the case study that we looked at, it was a major barrier for level traffic stress 1. It matters very little at high level of traffic stress, level stress 3 or 4. And then for level traffic stress 2, which is most adults, it's in between. It doesn't matter as much as segment level traffic stress. If you're trying to make a good bike network, pay attention mostly to the segments. On busy roads, provide separated bike lanes and other ways of protecting people from traffic. But still, intersections matter. There will be some intersections where you need to make a less stressful crossing so that the bike network will be complete, so people can get from one side of the road to the other.
Thank you very much, Peter. I have to skip the question part just to make sure that we will have enough time for the final presentation. So please reach out to Peter if you have any questions. Thank you, Peter. So last but not least, the final presentation on multimodal accessibility by Anindya Debnath.
Okay, I hope I'm audible.
For me, it is okay.
Perfect. And the screen I'm about to... Okay, looks good to everyone?
Yes, thank you.
Thank you for confirming. So, good afternoon, everyone. So imagine a small city resident looking at a map, and he or she is looking for places where the jobs are, or a grocery store, or a bus stop, and he or she thinks it's just only a short walk away. Then the sidewalk ends halfway there. On paper, the destination is accessible, but in practice, it may not be. And that gap between modeled and lived access is our study. I am Anindya Debnath, and this work is with Dr. Suman Mitra and Sebastian Jordan. So before we ask what bike share adds, we first need to be precise about what accessibility means. Accessibility is the organizing idea for this talk. It is not simply mobility or proximity. It asks whether people can realistically reach the opportunities they need. So we operationalize that idea to travel time. Here, accessibility means how easily people can reach destinations without a travel time cutoff using different transportation modes. So we get sort of an idea that the travel time, the travel modes matter, but most importantly, the network travelers can use matters. So the last point becomes especially consequential in small cities, because small cities need multimodal access, but they have thinner networks and fewer alternatives. A missing link can determine whether another transportation mode is usable at all. So if we roughly think about, go over the literature, then we end up seeing 3 more common constraints that make this challenge particularly difficult, because small cities often have limited sustainable options, and they also have implementation challenge and incomplete street and transit networks. adding a new mode doesn't automatically create a connected system. So bike share is attractive precisely because it promotes to bridge some of those gaps. Bike share can act as a flexible connector, extending the reach of walking and improving the first and last mile connections to transit, and that connections can translate into access to more opportunities. And prior work also suggests bike share can expand job access, including in suburban areas that are harder to reach by walking alone. Similar results have been reported for dockless systems, where dockless bike share has also been associated with increased job accessibility. All this evidence make bike share a promising small city strategy. But there is an important condition hidden inside that promise. Bike share's benefit depend on the infrastructure around it. People still have to walk to a station, ride a tolerable route, transfer, and complete the last segment. Pedestrian and bicycle infrastructure already influence usage, but does that infrastructure also change the accessibility benefit our traditional models report? So now the sidewalk network is therefore not background data. It is part of multimodal system. And if we take a look at these major city examples that show that the length of sidewalk network is relatively higher than the length of the streets in general or in total or at an aggregated level. Therefore, it is relatively safer to assume that people can walk on the streets to get to the transit stops while creating the network dataset when we try to measure network-based accessibility. However, that simplification becomes risky when sidewalks are sparse in small-scale cities. If we take a look at our study area, Fort Smith, Arkansas, that gives us a strong test of that risk. In Fort Smith, our inventory indicates sidewalk coverage is only about 25% of the total length of the street. If pedestrians can use every street in the model, the walking network becomes far more connected than the real one. That can inflate the baseline against which bike share is judged. And this leads directly to our two study objectives. We tried to contrast accessibility patterns across three different network scenarios: walk only, walk combined with bike, and walk combined with bike and transit. And we also considered two different pedestrian navigation assumptions. One is we let people to walk on the street versus we confined them to sidewalks. And finally, we assessed the accessibility impact of docked bike share system. And to test these questions in Fort Smith, we used the example from Ride for Smiley's bike share system here. Now, if we take a look at the study area, that study area combines Ride for Smiley stations, transit routes, and the Fort Smith's socioeconomic geography. Bike share stations concentrate around the urban core where opportunities and household conditions vary over short distances. Now, if we take a look at what kind of data we considered to measure our accessibility. But before that, if we take a look at the performance of the bike share system, the trip data also show that the system serves more than recreation. Recreation dominates overall in general, but among the carless users, shopping and dining rises from about 15 to 22% and mixed trips from about 5 to 9%. So we can see that everyday access, not just leisure, is therefore relevant in case of small cities as well. So if we take a look at the data set we use to measure the outcome, we assemble kind of like 5 different connected data layers, and we begin with jobs and point of interest. And point of interest, like you can think of any point of interest that are available on Google API, Street View API. So we took into consideration of this data, point of interest data, and eventually we then convert those destinations into a comparable opportunity index metric. For each census block, we normalize every opportunity category and aggregate the values. The example combines jobs, restaurant, and grocery access, and this creates one cumulative measure without letting the largest raw category to dominate. Next, we represent the physical cost of moving through the city. A 1 mile digital elevation model provides the slope information in our case, and that matters because grade changes both walking speed and the effort of bicycling. So we combine terrain with detailed street and transit attributes. The next one, the street and the transit layer includes road class, surface, lanes, routes, and stops. And these attributes determine which connections exist and their cost as well. For bicycling, we added a comfort and stress dimension, and we classify bike lanes using level of traffic stress criteria, including road type, speed, lanes, and parking conditions. So therefore, a mile of travel is not equally usable on every facility. And that classification produces the bike network as shown in figure number 7. The map distinguishes routes by bicycle stress and suitability, allowing less comfortable links to be penalized instead of treating all roads equally. So as you can see in the figure here, all the red streets that are high stress streets, and for biking, when we optimize the network, then anyone starting a trip from any census block would try to avoid these high stress streets and would try to pick some other alternative routes. And finally, we add the layer at the center of our research question. The sidewalk and trail inventory defines where pedestrian travel is actually permitted in the constraint model. It turns a walking assumption into an explicit network eventually. Now, with these layers, we construct 3 door-to-door scenarios. Scenario 1 is a direct walk. Scenario 2 adds bike share between 2 walking segments. Scenario 3 adds transit to that chain. These are door-to-door journeys. Every multimodal advantage still depends on the pedestrian links connecting the chain. And we calculate the time for each link rather than using a single generic speed. So for bicycling, travel impedance reflects distance, slope, and level of traffic stress. Walking speed is also slope adjusted. So we then include operational realities, for example, slower crosswalk movement, a 5-minute transit wait, an average transit speed, and 1 minute to unlock and return the bike. These assumptions keep the scenarios comparable and behaviorally more plausible, I guess. And these travel times feed the accessibility measure. For each origin, the sum of the opportunity index of reachable destinations weighted by the travel time impedance. In plain language, if more nearby opportunities create more accessibility, longer or harder trips contribute less. Now, if we take a look at the results, now we can see that what changes when pedestrian assumption changes. So each map pair here compares the same scenario and time budget. The map on the left allows walking on streets, and the map on the right restricts walking to sidewalks. Across walk only, walk bike, and walk bike transit, and at both 20 to 30 minutes of travel, the sidewalk constraint footprint is smaller. Even in many of the instances, is very much smaller and more fragmented. Multimodal travel still expands reach, but the missing pedestrian links prevent that expansion from spreading as far across the city. So this is something we are seeing when small-scale cities without enough connected sidewalk networks are likely to experience, even with an addition of different multimodal options. Now, if we take a look at the cumulative curves, that we can see that on the left, under unrestricted street walking, each added mode produces a larger step up in cumulative opportunity. By 30 minutes, walk, bike, transit reaches roughly 3/4 of the opportunity index. On the right, with sidewalk-only walking, it reaches closer to the mid-50s. The ordering of the modes remains the same. However, the accessibility opportunity level and the apparent multimodal benefit is lower when pedestrian access is realistic. Now, if we see the impact of bike share on multimodal accessibility, we can see the benefit also varies strongly by location. These curves show opportunity gain relative to walking as distance from the downtown increases. The largest gains occur near the opportunity-dense core, where a short bike connection unlocks many destinations. The gains then fall towards 1 as distance increases. Sidewalk constraints compress the curves and shorten the distance over which bike share creates a strong advantage. So what we learn from here is that the bike share station placement and pedestrian connectivity cannot be planned separately in small cities, especially. Bike share performs best when opportunities are dense and the first and last links actually connect. That brings us to that small city resident from the opening. We draw 3 conclusions. First, an ubiquitous pedestrian access creates an artificially generous walking baseline. And second, sidewalk constraints flatten measured multimodal benefit. And third, bike share adds the most value in opportunity-dense areas. And returning to our opening traveler, the decisive question is not whether a bike or bus is nearby. It is whether the traveler can reach it. Bike share is not a substitute for the pedestrian network. Its value is actually activated by that network. And a bicycle can extend a trip and a transit can accelerate it, but every multimodal journey still begins and ends on foot. If the first or last link is missing, the network on the map is not a network people can use. And thank you. I look forward to your questions now. Thank you.
Thank you very much, Anindya. So I think we have a question in the chat. Yes. So Peter has asked, how do you think results would differ with the third navigation assumption that allows people to walk on quiet local streets lacking a sidewalk, but not busy streets lacking a sidewalk?
Oh, that's a very interesting question. The results would differ with the third navigation assumption, people to walk on quiet local streets. I mean, it's sort of depend on how they are exposed to those kinds of distinct walking experiences, as well as how do they perceive the stress level associated with these kind of different street scenarios. So in my, if I think personally, in my opinion, if I were to take that walk, then definitely I would prefer to walk on a quiet street versus a more busy streets with more different kind of vehicular movement. So in that case, the accessibility would definitely be affected by the experience of those street conditions as well.
Okay, thank you very much. Just to make sure that we won't interrupt the next session, I have to conclude this session now. Thank you very much to all the presenters for their interesting contribution and everyone, the audience, for joining us. and I hope you enjoy the rest of BTR8 conference. Thank you.